everyone, and welcome to part 1 of our video series on the substitution rule. So, we want to ask ourselves a question. How do we deal with some more complicated integrals rather than the basic antiderivatives that we start with in Calc 1? So, how would we handle an integral like the integral of cosine of sine of x times cosine of x dx? So we don't already know any antiderivatives for this function, so we need another approach. And what we're going to do is make a convenient substitution and express the integral in terms of a new variable. So let's take a look at that. We're going to do a simple example. We're going to work through this example, and then we'll look at the rule a little more carefully and justify it, see why this happens, and move on from there. So, evaluate this integral. What I'm going to do here is notice that I know how to integrate cosine of a variable. That's not a problem. And here I've got, well, sine of x. So let's see what happens if I was to call sine of x just a variable, u. So that makes u, this variable, actually a function. It's the function sine of x. And what can I find out about this new function, u equal to sine of x? Well, its derivative with respect to x is cosine of x. Now, if I take my dx and multiply it across, what do I get here? I get that du equals cosine of x dx. And I notice, well, hey, that appears perfectly into my integral. So actually, the little du portions, which if we think back to our definition of the integral, is like sort of representative of this infinitesimal width of a rectangle. So we've got this little du, and this little du is always going to be cosine of x dx. So I can actually just go ahead and replace that cosine of x dx with du. So my integral here becomes the integral of cosine of u du. And the antiderivative for cosine is sine, so this gives us sine of u, and as always, plus a integration constant. But we're asking for the antiderivative of this function of x, so I have a little issue here, which is that I'm still in terms of u, but that's okay. We'll just plug u right back into our function. So u is sine of x, so this becomes sine of x plus c. So not too crazy. The important thing is that we set up this work off to the side clearly so that we make sure we don't make any mistakes in those little details. So let's take a closer look at this rule. This is really a theorem, and it states that if u equal to g of x is a differentiable function whose range is an interval I, and f is continuous on I, then the integral of f of g of x times g prime of x dx equals the integral of f of u du. So I want to just point out why we have these conditions, and that's one of the important things to understand about theorems, is that the conditions are there for a reason. We're building upon all this previous knowledge, but we know that these things only work under certain conditions. And in order to find an integral, usually, we're going to need some continuity, right? When we talk about the fundamental theorem of calculus, the most common formulation of it is in terms of continuity. And what does this tell us here? Well, if g of x is differentiable, then of course we know it's continuous. So since it's continuous and its range here is an interval I, for which f is continuous on that interval, that means that any value you get from g of x, you still get the continuity of the function f. So tells us we still have all the continuity we need from our whole function inside the integral there, and we don't have to worry too much about that. So, all right, let's take a look at a proof of this. So I'm going to talk about how to learn proofs effectively. Many students think that when they try to learn proofs, they should just try to memorize every word. And that's absolutely not very effective. Many students lose a lot of points on proofs because of that. So you first need to read the proof and make sure you understand the big idea. And then once you understand the big idea, go back and make sure you understand all the details, every little step. Why? Ask yourself why it's true. And then once you've done that, then you sit down and make a bullet point of the key points that you would need to remember. What's the big steps? And it should be a quick, short list. And then that's something that maybe you consider memorizing, but you need to be able to take that key information that should be maybe 5, 6, 7 words and use it to reconstruct the proof from understanding. So let's take a look. Well, we're going to start by letting f prime be equal to little f. So we've got a cap f here. So what we're saying here is just that big F is the antiderivative of little f. So then if we look at the function cap f of g of x, right? This is the composition of that antiderivative of f with g of x, and we take its derivative, then the chain rule gives us the derivative of our outer function, f prime of g of x, times the derivative of our inner function, g prime of x. So by integrating both sides of the equation with respect to x, what's going to happen here? Well, we're going to get the integral of cap f prime of g of x times g prime of x dx equals the integral of the derivative of cap f of g of x dx. So all we've done here is change the way we've formulated this statement a little by integrating both sides. And I want you all to notice that what we've really been dealing with here, this cap f prime, is f. So now this integral we have here is actually the left-hand side of the integral we're concerned with. Okay, so moving on. Well, we know by the definition of an indefinite integral that when we integrate a derivative, we get that original function back. So that gives us just, right here, f of g of x. So now we've got that the derivative of the integral of this derivative is f of g of x plus our integration constant c. And since we started out by defining u equal to g of x, then of course this right-hand side, f of g of x plus c, is the same thing as f of u. So f of g of x plus c equals f of u plus c. All right, so now what do we have? We have this big piece of information here. And we also know from earlier that this original integral we started with is equal to cap f of g of x plus c. And finally, the definition of the indefinite integral again tells us that cap f of u plus c is equal to the integral of the derivative of u, or the derivative with respect to u, I should say, of cap f of u du. So we have our starting integral is equal to cap f of g of x plus c is equal to cap f of u plus c, which is equal to the integral of the derivative with respect to u of cap f of u du. So if all of these things are equal in line, then of course they're equal to each other. That's the transitive property. So that tells us these two integrals are actually equal. And then all we're doing here in this last step is just rewriting cap f prime as little f, which is what it was by definition. Okay, so that's kind of a lot at once. and it might be hard to grasp the whole thing immediately, but let's go ahead, think about what are the key steps here that I would say recommend in the case of this proof that you try to get down the big idea of. So, key steps. First, let cap f prime be equal to f. That's the starting point. Without that, you've got nowhere to go from there. And then apply the chain rule on cap f of g of x. Integrate. All right, so what do? We applied the chain rule, then we integrated both sides. Then we substituted u. All right, we just plugged u in place of g of x, since that's how we defined u. And then in the end, we just rewrite our conclusions, and once again using the definition of an indefinite integral. So those are the 5 key steps. It's not useful to try to memorize a whole block of text like that, but if you go and you make sure you understand all of the key points, and then you can make yourself a quick, easy bullet point list of how to do this proof, it's going to be much easier for you to understand it in the long run and reproduce it through that understanding rather than through rote memorization. All right, so with all of that out of the way, let's go ahead and do some more examples. And I'm going to try here to illustrate my thought process as best as possible. So what it really comes down to with all of these problems is that you need to look for a function whose antiderivative you know. If you were to, say, replace a big block with just a single variable. And in this case, I think, well, I know how to take the antiderivative of the square root of a variable. And that's really what I've got here, right? This is the square root of something. So if I just had u there, this would be a lot better. Well, the algebra here is a little bit trickier. We take u equal to 5x plus 7. So that means my derivative of u with respect to x is just going to be 5. And when I multiply my dx across, that's going to give me du equals 5 times dx. But that doesn't quite work because I don't have 5 times dx here. So I have to tackle this one slightly differently. Really what I need to do is get all of my function in terms of one variable and constant values. So at this point, if I've already replaced u, all I really need to replace is the dx. So that's okay. I can just solve for dx explicitly by now dividing out the 5. So I get du over 5 equals dx. Okay, so let's rewrite our integral as the square root of u times du over 5. Now, of course, 1 over 5 is a constant, so I can pull that in front of my integral. And when we integrate square roots, we tend to rewrite them as a power function. So this is 1/5 times the integral of u to the 1/2 du. And as with our normal power rule for antiderivatives, we're going to add 1 to the power. 1 plus 1/2 is 3/2, and divide by the new power. And don't forget the plus c. All right, well, let's rewrite this a little better. This is 1/5 times, instead of dividing by 3/2, we'll multiply by 2/3. And instead of u to the 3/2, let's rewrite this as 5x plus 7 to the 3/2. We're just replugging our original value for u back into the function, and we still got that plus c. All right, lastly, this is 2/15 times 5x plus 7 to the 3/2. plus c. All right, let's move on to another example. Here we've got another square root, but in this case, it's not what's inside the square root that is causing us to have some difficulty integrating. Now, this example I think is a good one to point out that it's not always going to be immediately obvious when you're first learning these integral rules what to choose. So you sometimes have to be willing to try things, and you build an intuition. Sometimes it's really obvious, sometimes you get the same sort of patterns, but it's not always immediately obvious. So you have to think about what's my general principle, what do I want to do, and then maybe try something that will help you get there. And in this case, I think, well, what I want is a single function that I know the antiderivative of. I got to keep coming back to that idea. And I know that I know the antiderivative of cosine of u, right? I'd be fine if I just had y equals cosine of u. So I'm going to try that out. I'm going to let u be equal to the square root of x, which is, of course, x to the 1/2 power, and see what happens. Well, that means my derivative of u with respect to x is 1/2 times x to the negative 1/2 power. And that gives me that du is equal to, well, let's rewrite this with positive exponents. That's 1/2 times the square root of x times dx from multiplying the x across. And now what do I notice? Well, I see that I have dx over the square root of x here, which does look just like this. That 2 doesn't fit. So I'm just going to multiply the 2 across, and I get 2 du. It's okay if I have a constant in there still, as long as I get rid of any of the variable x, so that I only have one variable to integrate with respect to. And then that gives me 2 du equals dx over the square root of x. All right, so that means this is cosine of u times 2 du. Let's plug that all in. That's the integral of cosine of u times 2 du. I can pull my constant 2 out in front. That's 2 times the integral of cosine of u du. And that gives me 2 times sine of u plus c. And as always, we got to plug our value for u back in, so we get 2 times sine of the square root of x plus c. All right, great. On to another example. So this time we're going to look at the antiderivative for tangent of x. Now this one seems a little trickier because, hey, there's only one function here. How's that gonna, there's nothing plugged into it. How's that going to work? Well, we got to think outside the box a little. And if we recall, tangent of x is really just sine of x over cosine of x. That's called the quotient identity for tangent. And now this is where it gets a little tricky. So I can think, well, I want to replace a function with something whose derivative is going to show up in the formula here. So what function? Well, cosine of x. Well, sine of x has a derivative of cosine of x, so that seems like it would work. But then when I do my substitution, if you think it out a little, you would end up having like a du on the bottom or something here. It just wouldn't work out well. You could give that a try. I'm going to go ahead and skip that. And notice that, well, if I take the derivative of cosine, I do get negative sine. So I can work with that. So let's give that a shot. So we'll let u be equal to cosine of x. Then the derivative with respect to u is going to be negative sine of x. Now, this step here, I'm going to start skipping on future problems, so I just want to point out now, because you're going to do this so many times that's going to become second nature. So I'm just going to write du equals negative sine of x dx. In the future, I'll just skip from u equals cosine of x to du equals negative sine of x dx, just because one less thing to write about, and you're going to do it so many times. Okay, so du equals negative sine of x dx. Well, I need this sine of x dx to get replaced, since cosine of x is my u here. So what do I need to do? Well, if I multiply both sides by -1, I get negative du equals sine of x dx. So this gives me the integral of negative du over u. Now you might not really see it, because in these cases the composition of functions was obvious. If we look at our previous examples, we've got the square root of square root of x plugged into the cosine. We've got the 5x plus 7 plugged into the square root. We've got the sine of x plugged into cosine here. There is still a composition of functions here. It just doesn't look as obvious. The composition here is with the function 1 over u. So if we think about this, what we really have here, the 1 over cosine of x is really 1 over parentheses cosine of x. So it's really just the composition if you took f of x equals cosine of x and g of x equals 1 over x, then when you plug f of x into g, you get 1 over cosine of x when you replace x with f of x. So there's still a composition of functions built into this formula. It just doesn't look as obvious at first glance. So I just wanted to clarify that, because I want to drive home the point that whenever you're dealing with the substitution rule, you're really dealing with some type of composition of functions, even if you don't immediately see that that's what you're doing on first glance. All right, so I pull the -1 out in front, and this becomes -1 times the integral of 1 over u du. And that antiderivative is ln of the absolute value of u. And don't forget the plus c. So finally, this is negative ln of the absolute value of cosine of x plus c. All right, let's take a look at another example. Okay, so same kind of reasoning, a slightly more complicated problem than our earlier square root problem. We've got this z squared plus 1, and we've got a whole z out of here. And I think, well, I know the derivative of z squared is going to give me like 2z. Maybe I can work with that, because, hey, I know how to integrate the square root of u, so that's what I would like. So let's give it a shot. We're going to let u be equal to z squared plus 1. Maybe I can write that z a little clearer. Well, then when I take my derivative of u, I'm going to get 2z plus 0. And then we're going to have to multiply by dz, right? So when I multiply my denominator across, I'll get du equals 2z dz. And we've got z and we've got dz here. So if I want to make it just a little easier to substitute in, I can make this du over 2 equals z dz. So this becomes the integral of the square root of u times, and then z dz is going to be equal to du over 2. Okay, so I'll pull the 1/2 out in front. That means I'm integrating the square root of u, which is really u to the 1/2 power. That gives me 1/2 times u to the 3/2 power divided by 3/2 plus c, just like that previous example. And this becomes 1/2 times, instead of dividing by 3/2, we multiply by 2/3, times u to the 3/2 plus c. 2 over 2 cancels. And then when I plug u back in, I get z squared plus 1 to the 3/2 power divided by 3 plus c. All right, well, that's it for that example. And this will be our last example. So this one is definitely a bit trickier. So this one's not as straightforward. We have to take kind of an extra little step to solve this one. But once again, my first thought here is, hey, I've got this function inside. That's a composition. And if it was just u to the 7th, it'd be a lot easier. This x cubed is going to mess me up, but maybe I can work around it. And one thing I'd like to point out here is that this integral could be evaluated directly. But if you tried to evaluate it directly, it would require multiplying out this binomial to the 7th power, which is going to be huge. I mean, you're just going to have a ton of terms. It would take a very long time to do that by hand for sure. Less time by a computer, but definitely a lot of time if you had to multiply that by hand. So the substitution rule allows us to bypass that, and instead of having to do all that, written work of multiplying all of that out, we can instead do something sort of clever. So we're going to let u be equal to 2x squared plus 3. And then that'll give us du equals 4x dx. Now, if I think about this, x cubed is actually the same thing as x squared times x. And that's what I got to figure out how to get rid of that x cubed, all right? I can get rid of the dx with my du substitution if I was dividing out the 4x, but it's a little tricky. So let's try this. We'll take a slightly different approach here, and we'll do this substitution in 2 steps, which is a little strange, but it might, help see things a little clearer. So I'm going to just solve for dx this time and get that dx is du over 4x. And let's just see what we get left with. Remember, we can't integrate until we get rid of all of our x variables, but we might be able to at least see some other step that we can work through. So when I plug in u here, I'll get u to the 7th power. When I substitute dx, I'll get du over 4x. And notice, well, x cubed over x is just x squared, so that's progress. And 1 over 4 is a constant, so I can pull that out of the integral. And then I just have x squared times u to the 7th du inside. I got to get rid of that x, though. But that's okay because, hey, I've got an x squared right here, so I can actually just solve for x squared from my u substitution. It gives me u minus 3 equals 2x squared, and therefore x squared is u minus 3 over 2. And now I can plug that in place of my x squared. And now we're almost there. All right, I've got that constant 1 over 2. So if I pull that out front, that's 1/4 times 1/2, which is 1/8, times the integral of u minus 3 times u to the 7th du. And now, since the binomial here is only to the 1st power, this is a very easy multiplication to perform. So I can just distribute the u to the 7th times u minus 3 and get u to the 8th minus 3u to the 7th du. Now that's very easy to integrate, right? That's just regular old power rule. Gives us u to the 9th over 9 minus 3u to the 8th over 8. And tack on that plus c at the end. Well, don't forget we do have to substitute in our variable for u. So this gives us 1/8 times 2x squared plus 3 to the 9th power over 9 minus 3 over 8 times 2x squared plus 3 to the 8th plus c. One thing I'll point out is that if you had a computer evaluate this integral, most likely it would not use a substitution. Most likely it would brute force the multiplication and integrate that way. In which case the final answer you would get would look nothing like this final answer because it wouldn't be formatted into this form. Instead, you'd have just a huge, long, messy polynomial that would be very not fun to write down, but having the ability to use a U substitution, we can come up with a much nicer expression of the solution. Well, that's it for part 1. Thank you for watching.